Thanks for coming. Today we're going to be talking about sort of survival analysis and causal inference with survival-like outcomes. So think like time to die, time to hire, time to fire, that kind of thing. I'm Nathaniel Forde. I'm a data scientist with Personio and a sort of open source contributor to PyMC. You can find most of the code behind this talk on my website. Yeah, that should be enough. So the broad pitch of this talk is about trying to understand mediation analysis in the context of survival modeling. So there's kind of a tricky aspect of mediation analysis that comes up when you're thinking about what does causation mean in a mediation context. And there's two sort of primary views about causal inference in the literature. One is sort of privileges this view of probabilistic or counterfactual dependence. And then there's another view that causal inference is about sort of the unfolding of influence in time. They're both kind of intuitive and they lean on like different platitudes about causal inference. And so this talk is going to build a Bayesian dynamic path analysis in PyMC that tries to bridge both of those views. Following the work of Alan, he's Finnish. So the arc of this talk is a 3-act talk. We're going to first talk about sort of the puzzle of what mediation means in a causal inference context, competing risks, and why mediation sort of splits the schools of causal inference. Then we'll dive into the model. I'll show some of the illustrative PyMC code, and then I'll try and abstract the lesson or draw out the moral of the tale at the end. So the heart of sort of contemporary causal inference, both in the potential outcomes framework and the Pearlian do calculus, sits around this sort of counterfactual test of what a causal statement means. So they both kind of rely on this view that X caused Y means that Y would not have occurred without X. Okay, so like it's sort of operationalized in slightly different mathematics for the potential outcomes formulation of it and the do calculus, but it's sort of fundamentally the same thing. They're worried about counterfactual difference, so differences across counterfactual treatment regimes. It's an enormously powerful view for distilling like total effects. It starts to strain when we start to think about the decomposition of total effects across multiple pathways. And I want to talk about sort of 2 examples of why that decomposition is important, and then we'll focus on sort of the mediation case. So one example that's important in survival analysis is sort of a competing risks modeling framework where we try and look at, say, patient risks along a couple of dimensions. So like we might have a patient with 2 latent afflictions. Condition A stresses the heart, conditions B affects the lungs. Condition A progresses to the point that the patient dies. B never gets a chance to fire, so to speak, kill the patient. And then the counterfactual question here, or the counterfactual test, is would the patient have survived if condition A hadn't developed? The answer is no, because B would have caused the death regardless. So what this sort of points to is that there's like an endpoint view of like the causal question that zooms in on the direct and immediate cause rather than the overall developing process. So instead of the patient's health writ large, we're looking at the patient's response to a particular stimuli. So in one sense, this competing risks lens is like asking a granularity question. Where do we locate the cause and how far do we zoom out to assess the right circumstances? Mediation structures are a similar type of problem because they also push you towards trying to decompose the causal circumstance. But instead of having competing independent risks, you have a treatment potentially that works through multiple channels at once. So the example we're going to talk about is like an exercise program which sort of improves overall cardiovascular health, but it also inflames joints and sort of stresses cardiovascular health in a different way. So this like decomposition becomes important when you're trying to factor for how one treatment can have sort of multiple side effects, right? Or a primary effect and a side effect. Yeah, so and what's interesting in the causal inference literature is that mediation is tackled differently by the different schools of causal inference. So we're going to look at three views of what causal inference means and what a causal question answers. So the primary one, the first one here is the potential outcomes framework, which is very driven by no causation without manipulation as a sort of paradigm statement. So the idea is that if you're assessing a causal claim, you should have some sort of ideal experiment that could answer that. Mediation poses some problems for that because a very natural question to ask in a mediation context is what's the direct effect versus the indirect effect? And you try to get to that by what's technically called a cross-world counterfactual. So like two contrary counterfactuals at the same time. You need to hold the mediation fixed at one value and hold the treatment fixed at another. And there's technically no experiment you could run that would identify this causal effect. So mediation has a difficult operational meaning in the potential outcomes framework. In structural causal modeling, following Pearl, it's much simpler in the sense that they just define structural equations and they push the treatment effects through the model and sample the posterior predictive distribution. So mediation is a first-class sort of estimand in the structural causal modeling framework. In Allen's sort of process view of causation, the primacy is not on the endpoint, it's not on the natural direct effect or indirect effect, it's the trajectory of harm that evolves over time. So it's very much a time-indexed view of causal effect, and that mediation structure is sort of expressed algebraically within the model parametric structure of the model itself. So there's no direct cross-world counterfactual question that evolves. The focus is kind of like, it matters whether you're, say, killed by the werewolf or killed by the man. And it matters whether you're going to become a werewolf or not, right? So it's a view of the process evolving over time. So we want to build a model that can handle kind of all three of these views, or like estimands. And so we're going to build a dynamic path analysis model, which is traditionally estimated with recursive least squares, but we're going to build a generative version of that in PyMC. And we're going to replicate this example from the R package, dpasurv, which, it's that health example I mentioned earlier. So the first panel here on the left is the positive effect on cardiovascular health of your exercise regime. So it reduces the risk of cardiovascular death, so to speak. And then the middle panel is the sort of inflammation effect due to more extreme exercises. So it increases your risk of cardiovascular event. And then the final panel on the right is the total combined effect, right? So overall, more exercise is healthy, good for your heart, but there is sort of competing directional pulls throughout the process. And the value of the dpasurv model is that it tracks that time evolving effect through sort of time varying parameters. So what we want to do in our replication is build a model, a generative model in this case, which allows us to track the sort of structural relationships between the mediator, the treatment, and the health outcomes as it evolves over time. So like you have a sort of familiar Pearlian DAG context here, but what's important to understand is that we need to track the strengths of the relationships along this DAG over time. So the first DAG and the second DAG and the third DAG all have different strengths of relationships over time. And the evolution of those coefficients, in effect, is what we're kind of primarily trying to disentangle when we fit a mediation model over time. So we want to build this in PyMC. We want it to be a generative model with like a well-defined likelihood so that we can do counterfactual imputation. If you just fit this with recursive OLS, you get coefficient values, but you don't get the generative system that you can sample from and push forward. So that's sort of the main motivation. To build those trajectories and the time evolving parameters over time, we're going to use a Poisson likelihood. We're going to use a discrete time survival model. So we're going to discretize time, and we're going to smooth the trajectories with splines. So we have like a kind of discretize and smoothing step, which we will use to build the evolving coefficients over time. The discretization is fairly standard and pretty smooth. The use of splines and random walk coefficients or random walk priors on the splines, maybe less so. I have to kind of justify why we're using particular types of splines, why we want to smooth to this degree rather than that degree. In the code and the notebook associated, we sort of you run a sensitivity analysis for using different grades of splines. So like in this case, the best predictive performance through cross-validation is achieved by using 12 splines. But in other contexts, that might vary differently. The point is we're trying to model effectively a latent trajectory, and we're using splines to fit those latent trajectories. Yeah, so that's the code. Poisson likelihood is also reasonably familiar. It's an efficient likelihood for survival analysis. It's an efficient likelihood for a discrete time survival analysis. It allows us to make a generative model rather than a generating equations model. It's explicit because you directly model the baseline hazard as just coefficient values in your model, which is useful. This is the joint model of the two equations that we're interested in. I'm going to draw your attention primarily to the fact that these beta terms and alpha terms are indexed to t. So like there's a new parameter for each point in the time index. And they're sort of, they have inertia, right? So the mediator is predicted by its own lag. It's then fed into the hazard equation, which is then fed into the Poisson distribution. It's a hybrid model in the truest sense. It's got structural equations in Perlian language. It's got time-varying mechanisms in Allen sense, and PyMC is the sort of substrate that makes them all kind of cohabit together. Actually, I want to go back one thing to call out here. So what's crucial about this time-evolving DAG is that you have these structural relationships between the mediator and the outcome. And to make the claim that you are evaluating a causal relationship over time, you need to kind of make the claim that this is the only DAG that matters over that period. It's called a sequential unconfoundedness assumption, which can be quite a courageous assumption sometimes, but it's the assumption that you're effectively making. You're saying that the structural relations in your model are reliably sound throughout the period of evaluation, right? Yes, so in code, the model, or rather components of the model kind of look like this, right? So we have like the coefficients for the splines by the time and the number of time varying parameters we care about. We push it through a cumulative sum to get like a kind of random walk effect. We have the mediator equation, which is predicted from the lag of the mediated value. And then we have observation terms, so it's a likelihood as well. We feed that forward into the hazard equation, which we're calling eta here. So this is taking the mediator, pushing it through the outcome equation. And then we push that into the Poisson likelihood via a soft plus transform. That's a subtle change from the traditional Allen model, which has an identity link rather than a soft plus link. That means that the structure, the additive structure of our coefficients is in the latent space in our model initially, rather than the observed space. And from that, we kind of derive the direct, indirect, and total effects. And we sample the model. The good news is the model samples, it fits the data well, and it recovers the exact mediation structure we saw in the dpasurv graph that I showed at the top. We have like a positive effect, an improved cardiovascular health as the sort of direct effect, but we have an indirect effect which rises the risk of negative cardiovascular events, and then a total, broadly total positive effect over time. The risk rises around 100 days or so after increased exercise, which is kind of what we wanted to see, but it is at the latent scale. So we want to be able to force it into the outcome scale. So we sort of use posterior predictive imputation. So under different treatment regimes with a PyMC model, we can kind of intervene on the graph of the model, set all the treatment values to 1 or set all the treatment values to 0, push forward so that we can simulate how the hazard will evolve over time, for instance, or the survival curve. In the next graph, I'll show you the two hazards. So the left and right, or the left and middle plots here are basically the hazard coefficients under one treatment regime or under the other. And the graph on the far right is the relative risk, or the evolution of the relative risk statistic over time, which also shows a broadly positive or reduced risk effect, which is what we want to see. So like the nice thing about this whole generative model is that we kind of get two lenses on the problem. We get like the shape of the problem, or what I'm calling the shape of the problem at the sort of macro lens. which gives us the entire trajectory of harms as they evolve in the system. And we also are allowed to, or able to use sort of posterior predictive imputation to derive, using like G computation is another name for that thing, to derive like marginal estimands. So like hazard rates over time, or natural direct effects or indirect effects. And like in the context of like health evaluation, arguably, or at least I think so, the trajectory is often more important to decompose than just the marginal estimand. Because if you take the marginal estimand, like just reduced harm, you miss the actual negative effect of the treatment, right? And that can be more problematic than just your knees are hurting, for instance. So yeah, so Occam's razor is kind of like this call to keep your model as simple as it needs to be and no more simple than that. So you might, like, that's one lens on the problem is like get the endpoint analysis, is the treatment harmful or not? Yes, there's a 17% reduction, done. But I quite like this counterpoint to Occam's razor. It's called Hickham's dictum, which I hadn't heard of before, but it's like a patient can have as many diseases as they damn well please, which I think is a nice reminder to not to oversimplify prematurely. Refusing to decompose like a complex mediated risk structure is a real commitment, and it assumes that all the paths, all the treatment paths in effect all point in the same direction. This is like arguably an aggressive simplification. So the kind of idea here is that the DPA model that we've just implemented in PyMC is like an attempt to operationalize some of Hickham's thought here. We measure the direct path, we measure the indirect path, we get the total effect, and we see that the treatment is attenuated by an intermediating harm. And that's sort of like the broad rationale for why I think you should be attentive to like mediation structures in the survival context, right? It's not free, so like I have two slides now where like mediation structures are difficult to validate. They're sometimes difficult to identify. That's true for any approach to mediation, not just this Bayesian implementation I have here. But it's useful to try to decompose that risk, right? It's not just the total observed effect, it is the mediated harm plus the direct benefit. And if you have more complicated interacting effects, you should also model them, of course, too. But in this case, it's just like, it's a call to decompose the risk properly, which you can do quite neatly with a generative model in the PyMC context. Yeah, so yeah, you can just for calculating natural indirect effect, for instance, you do two imputation steps. You impute the outcome value when you set the mediator to a particular treatment regime, and then you take the predicted mediator value and push that through the next equation to get the sort of mediation step. Details don't matter too much right now, but basically don't oversimplify your mediation structures. Mediation is a real phenomenon, and it warrants modeling it properly. So broadly to sum up here, what we've built was a hybrid model. So we have Pearl structural equations. We have Allen's time-varying mechanisms. They're unified in PyMC with full posterior uncertainty. We get two kinds of estimands out of this. We have like the shape of the evolving trajectories, the time-varying coefficients, which give us the shape of the mechanism. We get G computation on top of that to derive any causal estimands we might care about, whether that's natural direct effect or natural indirect effects. So we get two scales. They're not symmetric for health problems. I think arguably the macro lens is more important and informative and actionable for doctors or HR executives if they're worried about attrition. Yeah, so the macro question I think here's the right lens for the problem, but probabilistic programming is the substrate that allows us to answer both, right? And so this kind of, yeah, so I'm kind of saying the same thing here. The shape is the most important one. It allows you to identify the realized process, which path is active, when, and what sign it has. You do want to sort of stress test your modeling here on mediation structures because they're so hard to identify properly. So you want to do like posterior predictive modeling checks. You want to do sensitivity analysis to robustness of implementation. Yeah, so like mediation structures are always an argument that you've got the right mediation structure right. That can be difficult, but at least making a probabilistic programming language makes it transparent, right? You're not hiding this inside the error term of the model. You have like structural components to argue about over and validate. So yeah, like this is sort of like a decision tree if you want one. Like if you just have a real simple experiment and you only care about the total effects on survival, just use a Cox regression. If you do need mediation, you can use structural equations. The modularity assumption in your structural equation model will give you a mediation estimate for free. If you want to see the big picture with time evolving effects, you probably want something like the dynamic path analysis model that we've just implemented here. You will see the evolution of time, and you'll also be able to derive the marginal estimands to your heart's desire. PyMC makes the whole thing answerable. Some references that you can find the initial post that motivated this talk on my blog. There's a couple of papers there. Ben, who's given a talk on causal inference, and I are writing a book on topics like this. So if you want more detail, do talk to me after. And that's it. Thanks, folks.